Okay, I'm going to get started. Thanks for the presentation and discussion earlier. It's always fun to think about the complexity of our analyses, and one thing that I like to stress in this course is that it's useful to understand as much as possible. We should try to understand what mixed effects models are, for example, which Murtaugh tosses out. We should at least try to understand them so that we know or have enough confidence to be able to say, actually, I don't need this, I can do this simpler analysis. And the other thing I'm trying to stress is that no matter what you are analyzing, complex or simple, always try to produce a graph that shows your model fit, just to make sure that everything's okay, that the numbers add up, and that you're not distorting the fit in some way. So that's one of the reasons why I like the Visreg tool in R. It's not perfect, but it helps you along those lines. Today I wanted to talk about likelihood. It's a topic you've no doubt heard of. Maybe you already have some idea of what it is. It's the basis for analyzing mixed effects models. And a lot of other analyses that we will encounter too, like generalized linear models, is based on likelihood. And likelihood is sort of the starting point for Bayesian analysis, which is a topic and we'll talk about later on as well. So here's an outline, and I'll give you a kind of a basic introduction to the concept. I'm going to let my cursor go away. Okay. I'm having trouble with full screen today. Here we go. I want to start with what is probability? So I talked about this earlier, but let's get it straight one more time. The definition of probability that most of our analyses rely on is called the frequentist definition. And the frequentist definition of probability is basically a long-run frequency. So if the same random trial were repeated over and over again under the same circumstances, the probability event is the long-run proportion of times that a particular event will occur. And a probability distribution is a list of all of the mutually exclusive outcomes that are possible from a random trial and their probabilities of occurrence. And one of the distributions that we learn in introductory stats and that used quite often in biology is the binomial distribution. So I'm going to just quickly review the binomial distribution because I'm going to use it to illustrate likelihood. So the binomial distribution applies whenever you have independent trials. Each trial has only two outcomes, which we can call success and failure. And the probability of success is the same in every trial, and that's little p. So if those conditions are met, then the probability of y successes in n trials will follow a binomial distribution. So here's an example for 18 trials with a probability of success in any one trial of 0.5. That's what the binomial distribution would look like. Success and failure, a lot of math was developed for games of chance, particularly when money was involved. And so they have sort of a charming jargon all their own, but don't take it personally. So the formula for the binomial distribution looks like this. What's the probability of, say, 5 successes in n trials? It's p, 0.5 raised to the 5th power, 1 minus p raised to the n minus 5th power. And then this part here is just the number of ways in which you can get 5 successes in a total of 18 trials. So it's just it's a counter. For example, you can get success, success, and then failure in the case of 3 trials. Or you can get success, failure, success. Or you can get failure, success, success. Those are all equally likely. And so when calculating the probability of y successes, you have to take into account not just the probability of getting y successes, a particular sequence of y successes and n minus y failures, but also the number of ways in which that can occur, the number of sequences of f's and s's. That's probability. What is conditional probability? So conditional probability is key to likelihood and also to Bayesian analysis. The conditional probability of an event is the probability of that event occurring given that a condition is met. And a vertical bar is used to indicate given in this context. So the probability that if you have two children, the second child is a girl given that the first child was a girl would be written like this, as a conditional probability. What's the probability that the second child is a girl given that the first child is a girl? Other conditional probabilities. What's the probability we see an elephant today given we are in the Serengeti? What's the probability we see an elephant today given we are in Manhattan? Those probabilities are very different. So the condition is important in establishing what probability distributions look like. So we use conditional probabilities in the following way in the examples that I'll show you today. What's the probability of getting 12 successes in n trials given that the probability of success in any one trial is 0.5? Fairly straightforward. What's the probability of 12 successes in n trials given that the probability is 0.1 instead? Well, that's a different probability. Likelihood is a conditional probability. And the way we use likelihood is to establish the value of some parameter of interest, a mean, a proportion, or some hypothesis. The likelihood of a population parameter equaling a specific value, given the data, is the probability of obtaining the observed data, given the value of the parameter. So we take the probability statement. What's the probability of getting the observed data given that the parameter of interest is p or rho or whatever specified value of interest? Invert that and you have the likelihood. Okay, probability of the data given the parameter is the likelihood of the parameter given the data. And it was R.A. Fisher who discovered that the extent to which data supports one parameter value or hypothesis against another is equal to the ratio of their likelihoods, or the difference in their log likelihoods. And that's how likelihood can be useful. I always tell people this fact here, if you're ever feeling particularly good one day, you've just got a paper accepted, or you finally, mastered this R4 loop, I just want to let you know that R.A. Fisher discovered the law of likelihood as a third-year undergraduate student. So likelihood is used a lot in biology, in all areas of biology. So if you type it into Google, a lot of the applications of likelihood in biology will be related to phylogeny, or phylogeny estimation. And I just have a quick example here to make a couple of points. This is a somewhat old paper by Ranella and Yang, but it used to be controversial which other ape humans were most closely related to. And that was more controversial because, once upon a time, because there was very little gene sequence data available. And here were sort of the three top models that were under consideration, that were most closely related to gorilla, that were most closely related to the clade that includes the chimps and the gorilla, or finally that were sister to the chimps. And the way the method was, the problem was solved, the controversy was finally laid to rest, is that a likelihood method like this was used. The researchers asked, based on the data, which in this case is the gene sequences, what's the probability of getting exactly the gene sequences that we see of all of these taxa if the tree is I? And to do that, you need a probability of, you need a sort of a probabilistic model for transition, change in gene sequences over time. A molecular clock, for example, is one of the assumptions. But with that model, it is possible to ask this question: what's the probability of getting the observed gene sequences if the tree is I? And that's the likelihood of tree I, given the sequences. And so the likelihoods for the sequence data that they presented in this paper, they calculated the likelihoods as follows. E to the minus 10149, which is a very small number. In fact, these are all very small numbers. And I show this example because I want to emphasize that what matters is not the likelihood itself, but the difference or the ratio of the likelihoods of these alternative possibilities. So how much more likely is one tree relative to another. And it was in this way that it was established beyond doubt, and it's been verified many times since, that we are the third chimpanzee. So I want to take the idea of likelihood and show how it works in practice. And I'm going to do it with a relatively familiar case, a proportion, in a sort of a simple choice trial, where an animal is provided with only two choices, and we record basically the number of successes. And then we'll use likelihood to estimate the proportion of successes in the population. So here's a picture of the head of a cabbage white butterfly, which you've probably seen flying around the city. And there's another insect riding on this cabbage white butterfly, which is a wasp, a very small wasp. And what this wasp does is that it sort of rides around on female butterflies. And then when the butterfly lands to lay eggs on a cabbage, the wasp climbs down and then parasitizes those eggs. So this is how it tracks down its host. And this group, Fatouris et al., carried out a series of trials to determine, can a wasp actually tell if the female butterfly that it might land upon is mated or not. The idea being it would certainly be advantageous if the wasp could distinguish a mated from an unmated butterfly, because one has got fertilized eggs and the other one does not. So they carried out a series of trials, 32 trials. And each trial involved presenting a single wasp with two female cabbage white butterflies, one an unmated female and the other one a recently mated female. And so each wasp is sort of, put at the start of a Y tube, and it can choose to go this way toward the mated and this way toward the unmated. And let's call a success that the wasp correctly chooses the mated butterfly. So they repeated this trial 32 times, and in 23 of those trials, wasps chose the mated female. So 23 successes, 32 minus 23 failures. And the question, one of the analyses that they carried out was, what's the proportion of wasps in the population choosing the mated female? So we want to use these data to answer this question. What is our best guess as to the proportion of wasps in the population that choose the mated female? And what we would like is not just a calculation of the proportion, but a confidence interval to go with it. How would we do that? One way we can do that is using likelihood. So the likelihood function for the binomial, so we have a series of 32 trials. Each of them is independent, different wasps, different butterflies, each trial. Probability of success is the same in every trial. So we know that the number of successes should follow a binomial distribution, with probability of success in any trial being p. P is unknown. And so the way that we would use likelihood to answer this question is we would ask, well, what's the likelihood of, a particular value of p, given the data that y equals 23 wasps chose the mated female. And to calculate that likelihood of a particular value of p, we invert it. What we're asking is, what's the probability that y wasps chose the mated females given p? And we know how to calculate this probability using the binomial formula that I just showed earlier. And for 23 successes out of 32 trials, it's p raised to the 23rd power, or 1 minus p raised to the 9th power, and then this combinatorics thing that just counts up the many ways in which 23 successes might be obtained in a run of 32 trials. So we don't know what p is, but we can say, well, what would this value be if p was 0.5? And that would tell us the likelihood that P is in fact 0.5. And so we would just plug P into this formula and say that probability would be, that likelihood is 0.00653. And in R, we could use the binomial probability function to ask what is the probability of 23 successes in 32 trials if the probability of a success at any one trial is 0.5, given that the probability of success in any one trial is 0.5. But how do we figure out which the best one is? Using likelihood, what we do is we go through them all. We consider all of the possible values of P. So we repeat the likelihood, but now for all other possible values of P, and here I've shown in a graph what those likelihoods are in the range from P equals 0.4 to P equals 0.9. And these likelihoods can get pretty small, so the way forward is usually to take the logarithm of the likelihood. And what the likelihood method does is it tries to find the value of P that maximizes the likelihood. And if you maximize the log likelihood, you're also maximizing the likelihood. So it's okay, and this is how you would use that, or you instruct R to give you the log likelihood rather than the likelihood. So we repeat this for many values of P. And then we connect the dots, and we get a curve that looks like this. So this is the log likelihood curve for these data. So just to reiterate, what we've done is that we use likelihood to estimate an unknown parameter using known data. So the parameter of interest is treated as though it's a variable. And we vary it from one end to the other. And the data are a constant. We have the data, and what we're going to do is vary P and then ask what value for the parameter maximizes that likelihood. So to emphasize, in this world, in the likelihood world, P is a variable, but it's not a random variable. This is not a probability distribution. It's just a function. The likelihood is a function of the possible values of P. I just said that. The maximum likelihood estimate is the value of P that corresponds to the peak in the likelihood or log likelihood function. And in sort of the likelihood world, we talk about the different log likelihoods for different values of parameters as a measure of how well supported that particular value is. The maximum likelihood estimate of a parameter is the value having maximum support, given the data. So in this case, we just sort of find the peak, and we obtain our estimate of the population proportion 0.72. So we would say 0.72 is the maximum likelihood estimate of this proportion. And the corresponding log likelihood is shown over there. Now, you might say, if you have your computer in front of you in your R console, you will have realized that 0.72 is just 23 out of 32. And so you might have thought to yourself, he's wasting our time because we already know what the proportion is. It's 23 out of 32. And of course, my reason for showing you this is because this isn't so mysterious for something as simple as a proportion. And secondly, I wanted to point out that 23 out of 32 is, the reason we use 23 out of 32 to estimate a population proportion from data is because it's the maximum likelihood estimate. The proportion of the number of successes divided by the number of trials provides a maximum likelihood estimate for a population proportion. So I've just shown this by example. I've shown it by mathematical proof. And it turns out that most of the formulas you use to estimate parameters are maximum likelihood estimates. So the sample mean, for example, is a maximum likelihood estimate of the population mean. Many of the methods that you already use sort of are based on likelihood. It can be shown to be maximum likelihood estimates. So it's already fairly well built into the methods that we use. Now what we would like is not only to estimate the population parameter, but we would like to have a confidence interval that corresponds to it. And in a likelihood world, here's how we can obtain a 95% confidence interval for our estimate, or for the population proportion. And it turns out when you're estimating just one parameter from data, in this case the population proportion, take the log likelihood that maximizes, corresponding to the maximum likelihood estimate, subtract 1.92, draw another line across, and then drop a line down where this curve, or this line, intersects the likelihood curve, and we have our approximate likelihood-based 95% confidence interval of the population proportion. And in that case, the confidence interval is 0.55 to 0.86. And I'll explain a little bit later where this 1.92 comes from. It comes from a chi-square approximation, and it's half the value of the critical value for chi-square based on 1 degree of freedom. So that's the first example, but a lot of the applications, a lot of the things that people use likelihood for are more complicated than a population proportion. So I've showed you a very simple example, but there are many cases, and in this simple example we already have a method for calculating the maximum likelihood estimate. It's just the number of successes divided by the number of trials. Well, there are many situations where we don't have a nice formula that represents the maximum likelihood estimate of something that we're interested in. And here's an example. The second thing that I want to illustrate with this is that you don't actually need to be a mathematician to use likelihood in your own data analysis. All you need is a formula for the probability distribution of the outcomes for a particular situation. So the likelihood formula for the proportion, you can find that on Wikipedia. I'm going to show you another example where there are two parameters that are being estimated for a particular situation, where there's no formula that gives you that maximum likelihood estimate, and where you need to do it by some kind of brute force. And the example comes from the television series The Game of Thrones, which some of you might have heard of. And I showed this graph. It's a photo I found online. There are museums, I guess, where this is some kind of an exhibit of some of the costumes worn by the characters in the television show Game of Thrones. And I thought I would show you this particular example. It's just the clothing that is being illustrated in this exhibit, but it's also kind of appropriate that these mannequins lack heads. Because when I looked at the causes of death of characters in the Game of Thrones, a certain pattern emerges. The first character is actually killed within 0.1 hours of his appearance on the show. The first decapitation occurs 0.01 hours later. And if you actually look at the causes of death, well, there's a theme. Hence the picture. So I've seen the show, but it's pretty violent. And I was so shaken after the first episode that I needed my emotional support daughter in the room when I watched the second episode. So in listing the causes of death, there are a couple of NAs, and that's because not everyone died in the show. There were a few characters left standing by the end. But But what I wanted to do with these data is, first of all, I extracted just the male characters, because it turns out the mortality rates are different for female characters. Which do you think is the higher mortality rate? Males have the higher mortality rate. And what I wanted to do is I wanted to, estimate something fairly simple, like the survival of males on this show. So this is a survival curve of the male characters based on all 8 seasons. So what this axis is 0 is the time at which a particular male character appeared for the first time on a show. And then the total length of the 8 seasons, I think, was something like 63 hours, something like that. It should be even. 64? I can't remember. 62 or 63 or 64. And what a survival curve is well, it is what it says. It's the proportion surviving. And likelihood is used to estimate parameters that describe these survival curves, and that's what we're going to do. So what I'm going to do, just to simplify it, is I'm just going to include in my analysis the characters that died before the end of the show. So I'm just forgetting about the ones that lived and just asking, of those characters that died, how long did it take them? So here's a frequency distribution of times till death. And time is measured in hours, TV hours. So 0 means that they died almost right away. But that could have happened in any season, at any time. But it does look like there's a fairly steep curve, and then not many survived till the very end. So what I wanted to do in this example was to fit a model to the data that would allow, the estimation of death rates and how survivorship basically can be described by simple parameters. And so one distribution that's used a lot for this is the exponential distribution. And that exponential distribution looks something like this. But it turns out the exponential distribution is not as good as the Weibull distribution at describing the shape of this survivorship curve. So it's like an exponential distribution, but it allows a greater variety of shapes. And if the shape parameter of the Weibull is 1, then it means the death rate is constant over time. It fits an exponential distribution and the death rate is constant. And so one of the reasons for trying to fit a Weibull might be to ask, well, is this parameter close to 1? Can the survival of male characters over the show be described as a process which is approximately constant and independent of time since first appearance? So again, no simple calculation will give you the maximum likelihood estimate for this. And I'm no mathematician. I didn't know the Weibull distribution, but I found it on Wikipedia. And it has Wikipedia is actually pretty good for finding probability distributions. It has 2 parameters, lambda and k. And what I did is I just did the same brute force that I showed you, brute force approach that I showed you with the wasp and butterfly example, where I just fit the data with a whole variety of values for lambda and k, and then asked, well, what's the best? What's the value that corresponds? So the Weibull probability distribution has again these 2 parameters, lambda and k. And the log likelihood calculation is simply the sum of the log of this for all of the individual data, t. So the ti are the actual data, the times till death of every individual character on the show that died before the end. And so I plug that into this equation, and I can ask, well, what's the log likelihood of this particular value of lambda or of that particular k. And I can do this in R because there's a Weibull function in R, of course there is. And so I can specify different values for lambda, different values for k. And it's exactly the same as I showed you already how to do for the earlier example. The only difference is that now I have two parameters to estimate rather than just one. And so I did kind of a grid search. And here I show you part of it. Here's different values of lambda. You know, the first search was very coarse. Different values of lambda from 0.1 to 1. And I could have gone larger than 1, which I did, but it doesn't all fit on the page. And then, you know, for each value of lambda that I tried a long list of values, possible values for k. And so then, you know, you sort of look at this chart and say, well, where's the maximum value for the log likelihood in this? And that's going to be somewhere in this column so far, at least if k is well close to the values which are illustrated. But try to imagine a large two-way grid. You could actually represent that with a contour plot on our graph, where the values for k that I tried are on one axis, and the values for lambda that I tried are on the other axis, connecting the dots as I did before. And now the likelihood curve is a surface rather than just a function, because now I have two parameters. But like before, so it's a contour plot, and the maximum likelihood estimate is here. That's where the height of this hill is located, and then these are just the contours are different sort of elevations, log likelihood elevations, so peaking here and then going down to above and below and to the left and to the right. So here's our value, our maximum likelihood value, our estimate for lambda, and it's not 1. So on the face of it, it looks like the probability of dying was not actually constant for individuals. So lambda hat was 0.54, and then scale, which is really sort of not all that useful, but it sort of like scale would be different if I changed it to days instead of hours. It's the shape parameter that we're interested in. So here's our original survival curve, and then here is the Weibull curve that drawn using the maximum likelihood estimates for scale and shape shown there. So I didn't have to solve anything. I didn't have to take derivatives to find optima. I just did a brute force search in R. And I didn't have to be a mathematician to do it. I just had to find a formula that worked and try a bunch of things. And here I was able to fit this curve, fit this model to the curve. So what does a lambda less than 1 actually mean? So an exponential fit where it's constant with lambda equal 1 would look sort of more like that. And the shape of this particular Weibull is more sort of scooped, especially near the front end. And what that means is that the worst situation to be in is to be a guy who has just recently appeared on the show. Because your chances of dying, disappearing from the show, are highest then. And if you survive, at least 10 hours on the show, it gets better after that. You're still going to die, but it's going to take a little longer. And so what this curve describes is a kind of natural selection, or maybe artificial selection, where characters, when they first appear, have a pretty high chance of being removed as, like they're defective in some way. They're not worth very much, so they're just meant as background violence. And they're limited quickly, whereas those that manage to survive 10, 20 hours, then their probability of dying slows. It certainly never goes away. Okay, so that's how to interpret a shape parameter in this case that's less than 1. It's again possible to generate likelihood-based confidence intervals. This is a joint 95% confidence region, so all combinations of lambda and k are they fall inside the sort of two-dimensional confidence region are shown by this ellipse here. So there's an equivalent when there's two parameters that you're estimating to what we already showed when there was just one. And so we can see that the 95% confidence interval is going to be somewhere between 0.46 and 0.62 based on this. A couple of other points I wanted to make before finishing with this example. There's a quantity called a profile likelihood function, and this is something you don't really want to do by hand, but you might run into it. And what it does is it says, look, we're interested in lambda, we're not really so interested in k. And the profile likelihood then says, well, that's just a nuisance. This is the thing we're most interested in. And so we end up producing, again, a two-dimensional curve like we generated, likelihood curve like we generated for the population proportion. But for every value of lambda that we try, we calculate the log likelihood of that particular value of lambda when k is set to its maximum likelihood value. So we put lambda, we fix lambda, we vary k and find the k that maximizes the likelihood, and we say that's the profile log likelihood of lambda equals that particular value. And we do that for all possible values of lambda. And so then we get a two-dimensional curve like we saw before. And in this case, the profile likelihood, 95% confidence interval, is 0.47 to 0.61. Second thing I wanted to just mention again is that the confidence interval is based on a chi-square approximation. And these approximations get better when sample size is large. They're not going to be very accurate when sample size is not large. Third, you don't have to do it by brute force. R has loads of tools for finding maximum likelihood estimates and drawing profile likelihoods and calculating confidence intervals. And if I get time, I will, I've just been learning one of these packages, and if I get time, I'll add one use of that to the workshop on Thursday. Otherwise, we're just going to be doing brute force stuff, like I showed you here. By the way, there's a, survival analysis is an industry, like literally an industry. And there's a package in R that will fit survival curves for you. And one of the reasons likelihood is used is that a lot of the data that is used in calculating the survival curve is called censored. So I don't know if you've ever heard the phrase censored data. But censored data, I don't know if I have the curve of it here. This original likelihood curve has a vertical bar every time an individual data point occurs that is censored. And what censored means in this case is that at this point in time, a character that had been on the show for 30 hours was never seen again on the show, and we have no idea when he died. So that's what censored data means. And all the characters that were left standing at the end are also censored because we don't know when they died. And so even though we don't know their times of death, we can still use them to estimate the survival curve. And that's because we know this particular character lived 30 hours. And so he can be used to calculate survival probabilities up to that point in time. So formal survival analysis makes use of that. Another reason why a likelihood formula is needed, another reason why computers are useful for calculating all these things. By the way, so I used the survival package to calculate the Weibull, the best fit Weibull curve for all the data, including the censored data, and the estimates are about the same. The last topic that I want to introduce is hypothesis testing using the likelihood framework. And this is also sort of a powerful application of the likelihood principle. And the idea is that rather than just have a continuous range of parameter values that we're interested in, we have maybe two hypotheses. Maybe a null hypothesis and an alternate hypothesis, or maybe just two hypotheses. So what I want to tell you about specifically is a method called the log likelihood ratio test, or the G test. And a log likelihood ratio test compares the fit of two models to the data and then asks, is the full model a better fit to the data than the reduced model? So the models themselves must be nested, and I don't mean nested factors as in a nested ANOVA. I mean one of the models must have a subset of the terms present in the other model. So we already are now used to this because we did this in the linear models section, where in our ANOVA table, every test in the ANOVA table involves an F test, which compares the fit of two models to the data. One, the full model, which contains the term of interest, and the other, the reduced model, where the term of interest is dropped. Those models are compared, and then we ask, is there a significant improvement in fit by including that term? In analysis of variance, in linear models, we use the F distribution, which exactly describes the probability distribution of outcomes under the null hypothesis. In the case of likelihood, we don't need to assume normality. We can use it for any probability distribution, such as the two that we use already in this lecture, the binomial and the Weibull. But the claim here is that exactly the same procedure holds, that it's always possible to compare a full model to a reduced model using the log likelihood ratio test. And it's completely general. It applies to any kind of data, any kind of model that you might fit that is a reduced form of a second model. So anytime two models can be nested, no matter what the probability distribution of the data, as long as you can find a formula to describe the likelihood, you can carry out a log likelihood ratio test. It's like a universal method for hypothesis testing. The p-value is approximate, but the approximation improves with sample size. And the formula for the log likelihood ratio test looks like this. G is the log likelihood ratio statistic, and it's calculated as twice the log of the likelihood ratio. It's very simple. And the ratio has the full model on the top and the reduced model on the bottom, given the data. So the full model always has more parameters than the reduced model, by definition. So this number is always greater than 1. And what we ask is whether this ratio is sufficiently large to reject the null hypothesis of no improvement in fit. And we use the chi-square distribution to decide that, in the same way that we use the F distribution in an ANOVA table. So under the null hypothesis, no matter what likelihood formula you're using, any application, it's completely universal. G is approximately chi-square distributed, and that approximation improves with increased sample size. And the degrees of freedom for that chi-square statistic is just the difference in the number of parameters between this model and this model. So I'm going to apply it once in the lecture just to the binomial data. So we're going back to the WASPs. So Fatouris et al. Carried out these trials, and they observed 23 successes out of n equals 32 trials. And they wanted to know, is this significantly different from a coin toss? In other words, is 23 successes out of 32 trials significantly different from a null hypothesis that the female wasps cannot distinguish between mated and unmated wasps? So the null hypothesis is that it's a coin toss, that the females, half the females would choose one and half the females would choose choose the other. And 23 out of 32 is just an outcome of a series of coin tosses against the alternative hypothesis that p is some other number besides 0.5. So in log likelihood ratio test jargon, both of these are model fits to the data. Here we're fitting a binomial distribution to the data where p is constrained to be 0.5. And here we're fitting a binomial distribution to the data where p is not 0.5, but where p is set to the maximum likelihood estimate. So reduced model, full model. That's what it means in this context. And p is the parameter we're interested in. So there's the formula gain for the log likelihood ratio. And then applied to the WASP example, the likelihood that p is 0.72 is on the numerator, and the likelihood that p equals the null hypothesized value of 0.5 in the denominator. So in the numerator, we estimated one parameter from the data, p, and in the denominator, we didn't estimate any parameters from the data. It was specified, p was specified. So the degrees of freedom for this G statistic would then be 1, because that's the difference in the number of parameters between the full model and the reduced model in this case. And the full model is always fitted with the maximum likelihood estimate mentioned. So we could calculate this ourselves. Likelihood of 0.72 in the numerator is this. Likelihood of 0.5 is 0.00653. Twice the log likelihood ratio is yields a G statistic of 6.336, and the critical value for the chi-squared corresponding to 1 degree of freedom is 3.841, and since this exceeds that value, we reject the null hypothesis. And half of this number of 3.841 is 1.92, which is the number that we used in calculating the 95% confidence interval.
And can you quickly go over again how the degrees of freedom was 1? How you calculate?
Yeah, the degrees of freedom is always the difference between the full model and the reduced model in the number of parameters estimated. And in this simple case, the null hypothesis estimates no parameters. The model is fitted to the data without estimating any parameters from the data. The p is specified by the null hypothesis. And under the alternative, p is estimated from the data. So there's a difference of 1 parameter between the null and the full, the reduced and the full. So the null hypothesis is rejected. So female wasps can actually tell mated from unmated butterflies. And this project went on to try to figure out exactly how they do it, what they detect on the female. And this is for you entomologists in the crowd, really, just a bit of science to indicate that this is actually a biology course and not a stats course. So when a male cabbage white butterfly mates with a female, he deposits benzyl cyanide, which makes females kind of smell like they unattractive. So that it's thought to be a mechanism by which males produce future matings by females with which they have mated. And the wasp detects that compound in the female, which is evil. You think? Yeah, it is. Log likelihood ratios are used a lot in biology. Actually, they're the basis of gene mapping. So I don't know if you've ever heard of a LOD score. If you've ever looked at data where people try to map traits on, like disease traits on the human genome using something like a QTL analysis. Maybe not. But if you do, you'll encounter something called the LOD score. And the LOD score is just a log likelihood ratio. And so how QTL analysis works is that at every position along the chromosome, it compares a full model where the full model is a model in which there's some association between disease state and genotype at that marker. In the sample of individuals that are in the study, and it fits a reduced model where the disease state is independent of genotypes at that marker. And then a log likelihood ratio is calculated to ask, how much more evidence is there for the presence of a gene near that marker that influences the disease state. And so basically you just calculate this degree of support essentially for the full model across the genome. And that was maybe one of the first analyses that discovered a major effect locus for schizoaffective disorder on human chromosome 1. Okay, that's likelihood, and we're going to apply what I've described to you today in the workshop this Thursday. So you are going to calculate likelihood surfaces. You're going to find maxima and estimate a few things just to get used to it. And I assure you it will be rewarding. Also, I sure hope you'll come and do it, because likelihood will be the basis also of the workshop that we'll do later in Bayesian analysis. One of the analyses will be duplicated there. The reading for next week is this: controlling false discovery rate when testing many hypotheses. And I already have presenters, I already have moderators. If you all have time now, come up to the front and I'll give you the rundown on what's expected. If not all of you can stay for a few minutes, then I'll grab you at the workshop on Thursday and do the same. Wait. And one more slide. Homework assignment number 2. The description, the details are on the homework page of the course website, but the idea is this. I want you to find some data from your lab, from your supervisor, and I want you to fiddle in your model, and then I want you to explain everything to me. Sound good? Okay, so there are criteria about how many variables and what kind of variables and so on, but all of those details are on the website.